Welcome to the Crazy Hat Chemist. So here we are with another awesome video. So hopefully you're with me. I don't know where you are or what you're doing, but good morning, good afternoon, and good evening. So we're going to continue, and this is going to be our third video, video number 3 on periodic trends. So we have done 1 through 12. That's our first video. And then we've done 13 through 18. And today we're going to start off with number 19, and let's see how far we go. I'm not really sure how far we'll get, but we're going to keep on going. So here we go. Without further ado, let's get moving. So periodic trends worksheet number 1, problem number 19. So let's scroll this on up here and let's zoom in here to look at problem number 19. Here we go. Problem number 19. And remember, you are watching the Crazy Hat Chemist. This is pretty crazy stuff over here. These are periodic trends. So number 19 says, which of each pair has a larger radius that is atomic size based on periodic trends? So we have calcium ion or magnesium ion. So what we're going to have to do is pull out a periodic table and compare these. So notice that all the ones that we are discussing here, we have 2 cations in this first one. So what we're going to do is pull out our periodic table, and we are going to be comparing the calcium ion versus the magnesium ion. All right, so here we go. So here's our periodic table, and it's the magnesium ion and the calcium ion. Okay, and so they are in the same column. That means that they are in the same group. These are the alkaline earth metals here. And which one is larger? Well, since they are both cations, they're both metals, they're both in the same group, we're going to figure out that as you go down a group, they get larger. So which one is larger? Calcium ion. Okay, fantastic. So let's see if we can pull that out here. And so we're going to circle the calcium ion is larger of the 2. All right. Now our next one here is B, the chloride ion versus the phosphide ion. So again, we're looking for the larger radius of the 2, and that's what we're looking for. So we've got either calcium or phosphide. So let's see, here's the calcium ion, and here is the phosphide ion right here. Okay, and again, these 2 are both nonmetals. Since they're both nonmetals, and they have the periodic trend charges of which they would be predicted to have, then I would just look at their periodic trends. And as you move to the right within a period, the size gets smaller. So consequently, the larger one of the 2 is the phosphide ion. Another way to look at this is that phosphide has gained 3 electrons, and it has a decreased effective nuclear charge in comparison to the chloride ion, which has only gained 1 electron, and it has more protons. So it's able to pull in those electrons even closer. So the phosphide ion is the larger of the 2. All right. Now the next one we're looking at is the copper 2+ versus the copper 1+, and figure out which one is larger. So really what we need to do is we need to find copper on our periodic table. It is right here. I'll just shade that in there, and I'm going to zoom out here so we can figure out our whole periodic table. What we're going to do is we're going to write out the electron configuration for copper. That's Cu. Then we're going to write out the electron configuration for the copper 1+ ion. Then we're going to write out the electron configuration for the copper 2+ ion, and then we're going to compare them. So what is remaining constant is the number of protons, and that is 29. So the Z, the atomic number, is 29 for both of these. Okay, and so hopefully that works for you. We're just going to start off here, and we're going to write out the entire electron configuration. So that is this is 1, 2, 3, and 4. That's all I'll need. So this is 1s1, 1s2. So I'm going to write that down, 1s2, and then 2s1, 2. That would be 2s2, just like that. Then it is 2p1, 2, 3, 4, 5, 6. 2p6, then it's 3s2, 3s2, then it's 3p1, 2, 3, 4, 5, 6, 3p6, then it's 4s1, 2, 4s2, and then it is a 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3d9. Okay, that is the electron configuration for copper, the element copper. All right, so now what we need to do is we need to do the electron configuration for the copper 1+ ion and the copper 2+ ion. So as you have a cationic charge, what is going to happen is you're going to be losing an electron for each cationic charge. That's the important component here to understand on this. So let's see if we can write that electron configuration out for you. All right, so let's do the electron configuration for the copper 1+ ion. This is the cuprous ion. So that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d, one less electron, so that is 8. Okay, let's write out the total number of electrons here for the copper atom. This has 0 charge here, copper atom, and there are 29 electrons. How many electrons in the cuprous ion? That would be 28 electrons. Okay, so we're going to keep that in mind. Now we're going to do the electron configuration for the cupric ion, and that is the 2+ ion of the two. So that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1 less than the cuprous or 2 less than the atom. So that would be 7. And then how many total electrons would be 27 electrons? Again, we're decreasing it by 1. Okay, so with all things being the same, that is, those are the number of protons are the same. The charges are different, right? And that lets us know that the number of electrons are different. Okay. So there's a nice 1-to-1 ratio with the atom. That is 29 protons and 29 electrons. That's really nice. Now we're going to go to the extreme here of the cupric ion, and there are 29 protons because, again, this is copper. And then there are 27 electrons. So 2 electrons have been removed from the atom state to find the cupric ion. So therefore, this one right here. Now we are only comparing here on this example here, we are only comparing cuprous and cupric. We're not comparing the copper atom, but I am writing this down so that you have a reference. Okay, so as you decrease the number of electrons, but yet remain or maintain the number of protons, then you're going to have a greater effective nuclear charge with this cupric ion. You're going to draw in these 27 electrons tighter, and therefore this one, the cupric, will be the smallest. And of the 2 ions, then the cuprous would be the largest. Which one is the largest of all 3 of them? Well, the atom. But that is not part of the question. So again, we are just comparing the cuprous versus the cupric. So that is the cuprous is the larger of the 2. Why? Because the effective nuclear charge on the cupric is greater and therefore draws in these 27 electrons tighter. Okay, hopefully we nailed that one down. Let's see if we can go to our next problem. Our next problem is nitride ion versus the fluoride ion. And so let's take a look at nitride and fluoride. Okay, nitride is right here at a 3- charge. Fluoride is right here at a 1- charge. These are the periodic trends of these ions based on their location on the periodic table. And since they are in the same period, then as one moves to the right within the period, they get smaller. So the fluoride is the smallest, the nitride is the largest. It has greater number of electrons and the least effective nuclear charge of 7. So which one is the largest? That is the nitride ion. Fantastic. Got that one nailed. Now we're going to do the iron ion, that's ferrous, and then ferric. Now this is very similar to what we did with the copper. And so maybe I'm hoping that you should be able to do this one without too much difficulty knowing what we did with the copper. And the copper has a 2 plus, a 1 plus, and a 0 charge. The iron has a 0 charge for the atom, of course, a 2 plus for an ion, and a 3 plus for the ion. And so the larger cationic charge is the smallest, and so the smallest one would be the larger cationic charge. All right, so we are looking for the 2 plus to be the largest here. So the smallest one is the largest cationic charge. That's the 3 plus. The larger one is the smaller cationic charge. That's the 2 plus. So there we go. All right, now the next one is the calcium ion versus potassium ion. And so we're going to cruise on over here and take a look at these two. The calcium ion is right here at a 2 plus. The potassium ion is right here at a 1 plus. And since both of these are metals, they're both cations. They have lost electrons respectively. And then we need to take a look at our periodic trends. And our periodic trends state the following, that as you move to the right, it gets smaller. And so which one is the smallest? The calcium ion. Again, which one are we looking for? We are looking for the larger radius of the two. So which one is the largest? The potassium ion of the two. So I'm going to write that down. Potassium ion is the largest of these two. Okay, just to verify this, they have the same number of electrons. That is 18 electrons, because calcium has lost 2, potassium has lost 1. But the effective charge on the calcium, because it has more protons, is larger. Thus, the larger effective nuclear charge will be the smallest. All right, that's another way to look at that problem. All right, so we're going to pull that off to the side, and then we're going to take, so just zoom it on in here so that you see all the answers for problem number 19. You got those. All right, so let's move on to problem number 20. All right, so problem number 20, let's scroll on up to that one, and it says the following for problem number 20, which of each pair has the smaller radius, that's atomic size, based on periodic trends. And again, we're looking at periodic trends, and we're looking now this time for the smaller of the two. So we're going to pull out a periodic table. We got potassium ion and lithium ion. So let's pull that periodic table out, and let's take a look at the potassium ion. That's right here at a 1 plus, and the lithium ion at right here at a 1 plus. They are both in the alkali metals, that is group 1. Okay, and the trend in size is as you go down a group, they get larger. So the larger of these two, and since they both have the same cationic charge, since they're in the same group, then the larger of the two is the potassium. What we're asked to solve for is which one is the smaller of the two. So that would, of course, be the lithium ion, because it's farther up on the periodic table. All right, fantastic. The next one here is B, and that's Oris or Auric. That's gold 1 plus and gold 3 plus. Okay, and so here we're talking about gold. And where is gold? Here is gold on the periodic table. Okay, so really what we need to be doing is writing out the electron configuration for gold, and the gold 1 plus and the gold 3 plus ion. So gold 1 plus and gold 3 plus ions. Okay, so let me zoom on out just a little bit so that you can see what it is that I wrote down. There we go. There we go. Gold Oris 1 plus, gold Auric 3 plus ion. So we're going to write out the electron configuration for both of these. I'm going to do the noble gas notation, and that would be xenon in brackets there like that. And then we have, after xenon, we have a 6s2. Then we have 5d 1, then we have to go to the F's. And so we're going to do 4F14. We're going to get through all of those, and then we're going to continue our D's at 5D2, 3, 4, 5, 6, 7, 8, and 9. Okay, and that is for the atom. So what we're going to do is we are going to remove an electron. And which electron? The largest principal quantum number, S and P, the outermost electron. So this 2 is going to become a 1. All right, and we're going to do the same thing here for gold 3+. We're going to have 6s2 and then 5d9 and 4f14. Okay, and if we're going to have the 3+ oxidation state for gold, we're going to remove these two. And so this is going to be a 0. This is going to be empty here. So you don't have to write that, or you place it as a 0. And then we're going to remove 1 electron here. Now, what I am writing are the predicted electron configurations. I'm not doing the actual electron configuration. So if you're looking at that, that might just slightly differ. Okay. So the question is, how many protons does gold have? 79. 79. How many electrons does the Ors, or the gold 1+ ion, have? 78. And then how many electrons does the auric, or the gold 3+ have? Well, 3 less, so that would be 76 electrons. Okay, so which one, the question is on this problem here, which one is the smaller of the two? And that is, the smaller of the two has the greatest effective nuclear charge with the least number of electrons. So they have this the same effective, the same number of protons, but the auric, the gold 3+, has fewer electrons, so it's going to draw those electrons in tighter, and so therefore that one will be the smallest. So we're going to write the smallest one right here as the gold 3+. All right. A little bit more complicated explanation as when you get to the same element with different charges. You're looking at effective nuclear charges. All right, the next one is the phosphide and the nitride ion. They're both a 3+, so let's take a look at those. That is phosphide, that's 3-, nitride, that's 3-. Okay, and as we go down a group, or a column, and since they are in the same group or column, the larger one is at the bottom and the smaller one is at the top. So again, this question is which one is the smallest? So that would be the nitride ion would be the smallest. All right, fantastic. All right, so let's move on to the next question here, and that would be 21. 21 says the following: order in increasing size, starting with the smallest, going to the largest based on the periodic trends. Vanadium 0, vanadium 3+, vanadium 5+. By the way, the vanadium ion has almost more than any other element as far as the cationic charges. It has an immense number of cationic charges. So vanadium is right here, element number 23. And what are we comparing? Vanadium 0, vanadium 3+, vanadium 5+. So we're going to write out the electron configuration for vanadium, 0 charge, that's the atom. Vanadium 3+, that's the cationic charge of 3+, and vanadium 5+, that's the cationic charge right there. So we're going to write out the whole entire electron configuration of this. Hopefully you have you've done electron configuration, so hopefully this won't be so bad. So we're going to do 1s2, 2s2, 2p6, 3s2, and 3p6. Then we have 4s2, and then 3d3. Okay, that is for the atom of vanadium. And vanadium has 23 protons in all of these because it's vanadium. That part doesn't change. And how many electrons in the vanadium atom? Well, you should be able to count up the superscript numbers, which of course should add up to 23. So 23 electrons. So it's a nice 1-to-1 ratio between the electrons and the cationic, positive charge in the nucleus. That's the number of protons. Now let's do the vanadium 3+ ion. So this will be 1s2, 2s2, 2p6, 3s2, 3p6. And now here's the tricky part. So what you are removing is the outermost electrons first. The outermost valence electrons are the 4, which is the largest principal quantum number. So it's actually 4s naught. So those 2 electrons have disappeared. And then it is 3d, since I'm going to remove one more, 3d2 instead of the 3. So how many electrons does this have? This has 20 electrons in it because there are 3 less electrons. Okay. All right, next one is vanadium 5+ ion. So 1s2, 2s2, 2p6, 3s2, 3p6. And again, the 4s naught is not there. We have removed both of those. And we're going to remove 2 more electrons. And so it will be 3d naught. And then these are gone. So you don't have to actually write those. Okay. So 6, 12, 13, 14, 15, 16, 17, 18. So this has 18 electrons as one would expect. Okay. So which one is the largest? Which one is the smallest? We're supposed to write this in order. Okay. And we're supposed to write this from smallest to largest. Okay, so the smallest of the 2 has the greatest effective nuclear charge. That is the one, there's the constant of the number of protons, but the number of electrons has differed in each one. And so you have removed the most number of electrons of the outermost shells as possible with the vanadium 5+, so that has the greatest effective nuclear charge. That is the smallest. So I'm going to place the vanadium 5+ ion right here as the smallest. That's going to be my first one. Then the next one in the middle is the vanadium 3+. And so that's vanadium and a 3+. And then finally, the last one, which is the largest, is the vanadium atom. And so that's vanadium that's a 0 charge. All right. So that is number 21 for you. And hopefully that one worked out well for you too. And hopefully you're understanding that and the cationic charges and what's happening with all of these. All right, let's move on to problem number 22. Okay. All right, so problem number 22, it says the following. It says there is a large jump between the second and the third ionization energies of magnesium, and there is a large jump between the third and fourth ionization energies of aluminum. Explain these statements. Okay, so what we need to do is pull out another periodic table. Of course, that's why this whole unit is periodic trends, because we are talking about periodic table and the trends therein. So we're going to pull out this periodic table and take a look at this here. All right, so the question is, why is there a large jump between the second and third ionization energies of magnesium? So we're going to take a look at where magnesium is. Magnesium is right here. Okay, so as we take a look at magnesium, we could write out the electron configuration for magnesium, and I'll do a noble gas notation of that one. So you're going to go up one period and slam it far to the right. That would be neon. So magnesium is the element that we're doing, and neon is the noble gas prior to magnesium, and then after neon, it's 3s2, 3s2. So that's the noble gas electron configuration for magnesium. All right, so the question is, why is there a large jump between the second and third ionization energies for magnesium? So let's take a look at the electron configuration and then understand what the concept is for ionization energy. So ionization energy is the removal of electrons from the gaseous state of either an atom or an ion. Okay, and so this is the atom. So the removal of these 2 electrons is relatively easy. Why is that? Because magnesium is in group 2, the alkaline earth metals. And how many valence electrons does magnesium have? 2. So why are you going to remove So the first valence electron is lowest in ionization energy. Okay, then you have magnesium with 3s1. Then the second ionization energy is going to be a little bit higher than the first. Why? Because it's harder to remove electrons with each subsequent electron removal. Let's kind of zoom in on here and take a look at this a little bit closer. Sorry about that. So the first ionization energy is the lowest. The second ionization energy is higher than the first, but still relatively low. Why? Because now you are finally forming the predicted cationic charge for the magnesium ion, which is a 2+. Okay, so that's very critical. So why is there a large jump between the second and third ionization energies? So what you have removed at forming the 2+ cation is a noble gas electron configuration of magnesium, which is the magnesium 2+ ion. What kind of electrons remain? These are core electrons, and core electrons are exceedingly difficult to remove. So there's an immense jump in the third ionization energy for magnesium, because that is a core electron of which you are attempting to remove. And this is why magnesium only forms the 2+ cationic charge, right? All right. Furthermore, as you are removing electrons, you're increasing the effective nuclear charge. That's why it costs more energy for each of these electrons, right? There's a nice 1-to-1 ratio for the first ionization energy, then the second ionization energy. You've already removed an electron, so the effective nuclear charge has increased, all right? And it's gotten smaller. Those electrons are closer and tighter to the nucleus. All right, now what we're going to do is we're going to take a look at aluminum, and aluminum is over here. I'm going to give myself a little bit of space here to write all this out here and put a little bit of mass down. Look at that. I got 100 grams and 200 grams of placing the mass down. All right, let's take a look at aluminum, and we're going to write out the electron configuration for aluminum. So aluminum has a noble gas electron configuration of neon, then it's 3s2 and then 3p1. Okay, so this is the aluminum atom. So the first ionization energy for aluminum. So here's aluminum, the first ionization energy for aluminum. We are going to remove which electron? This one right here. So the first ionization energy for aluminum is right here, and that is a very low number. Why? It's a valence electron, okay? Then the second ionization energy is one of these electrons, since all of this 3p shell has been removed. And so the second ionization energy is higher than the first. Why? The effective nuclear charge has increased. Then the third ionization energy is going to finally remove both of the last electron in this shell. And that ionization energy is going to be higher than the second, so third ionization energy for aluminum. Now you should see what remains, just like what we had on the previous problem, are core electrons. Core electrons are interior electrons. I've removed the three valence electrons for aluminum, and at this point in time, you're forming the aluminum 3+ cationic charge, which is the predicted charge for everything in this column, and aluminum is in that column. So the fourth, so why is there a big jump between the third and fourth ionization energy? So there's a large jump in the fourth ionization energy for aluminum. Why? It's because the effective nuclear charge has increased so much, and furthermore, that is a core electron, most importantly. Okay, so core electrons are very, very difficult to remove. You don't want to remove those except for a large cost. All right, so hopefully we got that nailed down. So let's cruise on to the next problem, and hopefully you've written all that down, and we're gonna peel this away and cruise on to the next problem here. And just so happens we're moving on to the next sheet of paper here, the back side of the worksheet. There are a lot of problems here. There's 45 problems, and I don't think I'm going to be finishing up these 45 problems in this particular video, but we will keep on going on these videos so that we've got them all done for you. All right, so the next problem here is number 23. Consider the ions and periodic trends. We have nitride ion, sodium ion, oxide ion, fluoride ion, magnesium ion. And we're going to compare the number of electrons in each, order in decreasing size, order in decreasing ionization energy, and order in increasing electronegativity. So I want you to make sure that you pay particular attention to some key words, okay? And so we're doing in decreasing size. So make sure that you look at that, and that is a very important term there. And then same with decreasing ionization energy and increasing in electronegativity. So those words really mean a lot. So what we're going to have to do is take a look at a periodic table and come up with these based on the periodic trends. So I'm going to peel over a periodic table and take a look at these with our periodic table. And I'm going to zoom on out because otherwise we're not going to be able to do this problem here. All right. So this is what we've got. We've got our periodic table, and we need to figure out on the periodic table what we are looking at. So we are looking at the following: the sodium ion, the magnesium ion, the fluoride ion, the oxide ion, and the nitride ion. Okay, and so hopefully you can see those. I'm going to highlight each of these so that you understand where they are located on the periodic table and what their charges are. Okay, so let's see if we can do this here real quick here. All right, fantastic. So I want you to see that they are not in the same period. They are actually alternating periods. Okay, sodium has its predicted charge of 1 plus, magnesium ion has its predicted charge of 2 plus, nitride, its predicted charge of 3 plus, oxide, its predicted charge of 2 minus, and fluoride, its predicted charge of 1 minus. So I'm going to zoom in just a little bit so we can cover everything right there. Hopefully you can see that a little bit better. And zooming on in a little bit, tiny bit more. Here we go. All right, so what we can see here is the following. There we go. I love my little weight there. It's so much fun. Okay, the crazy hat chemist got 100 grams. All right, so what we are looking at here is a number of different components. What we are looking at is compare the number of electrons in each. Okay, so for example, sodium has lost 1. So how many electrons in the sodium ion? 10. So we'll write this down. Sodium ion has 10 electrons. Okay, the magnesium ion has lost 2. It had 12, it lost 2. Magnesium ion, how many electrons? 10 electrons. Okay. Fluoride ion has gained 1. So 9 plus 1, that's 10. So fluoride ion, 10 electrons. I'm thinking that you're already seeing the pattern here. Oxide ion, it had 8 electrons. It's gained 2. That's a total of 10 electrons for the oxide ion. Nitride ion. Nitride ion has 7 electrons and it has gained 3. So the nitride ion has what? 10 electrons. Oh my gosh, this is an amazing thing. This is actually a very, very special case, and this is called isoelectric. And I'm not sure if you're familiar with this prefix iso. Iso means the same. And electric is number of electrons in this case. So how many electrons in each of these? They all have 10 electrons. In fact, they have the same number of electrons as neon. Neon is kind of like the gold standard comparison to all of these. because it also has 10 electrons, but it doesn't have a charge. All right, now we've got part A done, and part A was compare the number of electrons in each. They all have 10 electrons, and that is called isoelectric. Okay, so that's a term that we're going to come across in a little bit later, and then we'll refer back to these. Okay, now we're going to order in decreasing size. So as we look at these in order of decreasing size, we're going to find the one that has the largest cationic charge, that's magnesium ion, and that would have the greatest effective nuclear charge. It has 12 protons in the nucleus, and it has the fewest number of, it has lost electrons, so it has lost shells, and its effective nuclear charge has increased. So magnesium ion is going to be the smallest of the entire group. Then if I go at the far other end, the nitride ion has gained 3 electrons, so its effective nuclear charge has decreased, and therefore it has gotten bigger. The electron-electron repulsion in the outermost shell has increased, and that pushes the electrons farther away as well. So we're writing this in order of decreasing size. So which one is the largest? The nitride ion. So that would be nitride ion is the largest size. And then, so that would be the largest in terms of size. And then it's the oxide ion. Then it's the fluoride ion. And I'm going to write neon here, even though it doesn't have it on this problem. I'm going to write neon just as a kind of rough comparison, because it has a 1-to-1 ratio of the protons and the electrons. And then we have the sodium ion, and then the magnesium ion. Okay, smallest in size. Fantastic. All right, so now we've got size. So that was part B. The next part, which is part C, is decreasing ionization energy. Okay, now I don't know if you remember this from watching my lecture video series, but here is what's happening. So if we look at our periodic trends, in terms of size, we have increasing size as you go down a group, decreasing size as you go to the right, so therefore increasing size as you go to the left. So size is very large down here at the very lower left-hand corner of the periodic table, and that would be francium is the smallest, sorry, excuse me, largest. Francium is the largest in terms of size. So the question is ionization energy. Ionization energy is actually the opposite trend. So large ionization energy is in the upper right-hand corner. So that would be like, for example, fluorine. So size and ionization energy are direct opposites of each other. So if I am going to write this in order of decreasing ionization energy, what I'm going to do is I'm going to take my size comparison and I am going to flip it. So the largest in ionization energy would be magnesium ion, then sodium ion, and I'm going to write neon just as the direct comparison to them all here. And then we have fluoride ion, oxide ion, and nitride ion. And this is an order of decreasing ionization energy. So decreasing ionization energy, okay? And it is a direct opposite that of size, all right? Okay. Now, the next question, the last part of this one, is increasing electronegativity. So increasing electronegativity is the same trend as ionization energy. Okay, so notice that we have decreasing ionization energy and then we have increasing electronegativity. So increasing electronegativity is opposite of decreasing ionization energy. Increasing electronegativity is the same as decreasing in size. So I'm going to take my size comparison and I'm going to rewrite that or flip the ionization energy example. All right, so now I'm going to have, and again, the direct comparison so that you got that neon in there, even though that was not in this problem. All right, so now this is in order of increasing electronegativity. So increasing electronegativity. So increasing electronegativity right there. So now you should see all of these right here on the sheet of paper here. We have, what do we have? We have a size, decreasing size. We have decreasing ionization energy and increasing electronegativity. Fantastic. Hopefully that's looking fantastic and really super special for you. All right, now we're going to take a look at the next problem and let's see if we can hammer that one out. That would be problem number 24. All right, so here we go with problem number 24. And problem number 24, it says the ions potassium, calcium, chloride, scandium, and sulfide have the same total number of electrons as the noble gas argon. Organize these according to based on periodic trends, increasing size, decreasing ionization energy, and decreasing electronegativity. All right, so we're going to do all these. This is very similar to problem number 23. So hopefully you understand that component of it. We're almost looking at the same thing. So again, what we're going to do is we're going to pull out a periodic table. Hopefully you remember potassium ion, calcium ion, chloride, scandium, and sulfide ions. And we're going to take a look at those on our periodic table. So let's find our periodic table. We're going to find these ions and their associated charges. So we have potassium ion, that's going to be a 1 plus. We have calcium ion, that is a 2 plus. Notice that these are periodic trends. We have the scandium ion as a 3 plus periodic trend, yet again. And then the chloride ion, 1 minus, sulfide ion, and a 2 minus right there. And these are all relatively compared to argon, of which has right there. Okay, so what we are doing is I'm going to highlight these so that you see which ones we are comparing. We're comparing potassium ion, calcium ion, scandium ion, sulfide ion, chloride ion, and I just wrote in the argon there just as that direct comparison. Okay, you should see that all of these, as the question read, have the same number of electrons. So the same number of electrons is that of argon. And I'm just going to verify that for you. How many electrons in argon? 18. Chloride has one more than the total than the number of protons. So 17 plus 1, that's 18 electrons. Okay. Sulfide has two more than the number of protons. So 16 plus 2, that's 18 electrons. Potassium has one less. So that's 18 electrons. Calcium has 2 less, that's 18 electrons. Scandium has 3 less, that's 18 electrons. No way, I can't believe it. These are called isoelectric, right? So if they are isoelectric, and they are in this example, what we are going to do is order this in order of what? Increasing size. So what is the smallest? The smallest is the one with the largest cationic charge. And the cationic charge is a 3 plus. That is the one with the greatest effective nuclear charge. It has lost the most number of valence electrons. So the largest one is the opposite of that, and that's the one with the greatest anionic charge. It has gained the most electrons. It has the greatest electron repulsion in the outer shell, and it has decreased its effective nuclear charge. So we're supposed to write this in order of increasing size. So increasing size would be the smallest size first. So that's the scandium ion, then calcium ion, then potassium ion, and then I'm going to put argon in here as a comparison, then the chloride ion, and then the sulfide ion. So this is in order of increasing size. So this is the smallest size and the largest size. Okay, all right. Fantastic. The next question is decreasing ionization energy. So I have increasing size, and so size and ionization energy are opposite of each other. But this is increasing size, and then the question is decreasing ionization energy. So decreasing ionization energy is the same as increasing in size. So I'm going to write this pattern down. Okay, and this is decreasing ionization energy. So decreasing ionization energy. So this has the greatest ionization energy. And again, I'm putting argon in here just as a comparison. And so this is decreasing ionization energy. Okay, cool. All right, the next one is decreasing electronegativity. Okay, so decreasing electronegativity is the same as decreasing ionization energy. So hopefully that makes sense, right? Okay. All right, so we've got scandium, calcium, potassium, argon as a comparison, chloride, sulfide. Okay, and so this is in order of decreasing electronegativity. All right, fantastic. All right, that is perfecto. Now we're going to go to the next problem here, and the next problem here is problem number 24. No, excuse me, 25. Here we go, 25. Okay, so number 25 says the following. It says, arrange the following atoms in order of increasing size, atomic radius, based on the periodic trends. SR, so we're going to find SR, that's right here. Okay, and then we're going to find SE. SE is right here. And then we're going to find K, that's right here. And then we're going to find BE, that is right here. And then we're going to find F, and that is right here, just like that. So again, the question is, arrange the following atoms in order of increasing size, atomic radius. So increasing size. So we need to figure out which one is the largest in size. Okay, so the largest in size, so your trend is as you go down a group, you get larger. As you go to the right, you get smaller. Okay, so the largest in size is going to be the one that's furthest to the lower left-hand corner, that's strontium. So we're going to write this of increasing size. So that means that strontium is going to be the largest in terms of size. Largest size. Okay, so we've got that one covered because it's in the lower left-hand corner. Okay, then what we're going to do is we're going to be comparing the next largest in size. Okay, the next largest in size, we're going to see potassium and selenium are in the same period. So as you go to the right, you get smaller. As you go to the left, you get larger. Potassium is here. So potassium would be the next one in terms of largest in size. Then we have selenium, since that's in the same period. It's in period 4. So then we have selenium. Then we've got potassium, we've got selenium. Now we got beryllium and fluorine. Okay, and of these two, which one is largest? Well, the one that's furthest to the left. Or which one is the smallest? The one that's furthest to the right. So beryllium would be our next one in terms of size, and fluorine is our smallest in size. Okay, All right, fantastic. I'm liking that one. That one's looking really good too. That was number 25. All right, let's give that a hoot and a holler because we got that one nailed. Okay. All right, so now we're going to do the next one, which is number 26. Okay, number 26 says the following. Arrange the following atoms in order of increasing size. That's atomic radius based on the periodic trends. We've got sodium, yttrium, barium, and chlorine. So we're going to pull out another periodic table. Got to do that, of course. So a new periodic table, and we're going to just write out where these elements are on the periodic table. Okay, so what elements do we have? We have sodium, yttrium, we have barium, and we have chlorine. Okay, and the question is in order of increasing size. So again, as you go down a group, they get larger. As you go to the right, they get smaller, larger. That's in terms of size. So which one is the largest? The largest is the barium. Which one is the smallest? The smallest is the chlorine. So we're going to write chlorine as the smallest size. Then the next one from that would be sodium. Then the next largest one would be yttrium. And then the next largest one and the final one, the largest one, would be barium, largest size. So I've written this in increasing size order. So hopefully you got that one. That's number 26. All right. So by the way, I just wanted to take a quick little station break before we go on to problem number 27. And I am the Crazy Hat Chemist. This video is brought to you by and sponsored by the Crazy Hat Chemist. So hopefully that works well for you. I hope you have a great afternoon and good morning and a good evening. And I will see you next time. So we will do another one after this one. This is part 3. We'll have to do a part 4 at least. So we'll see you for part 4 next time. Bye for now.